Hello and welcome. My name is Vinny Minning, and I'm the project manager of Metal Engineering Consultants. Our team was tasked with designing the retaining wall and foundations for SDSU's new North Life Sciences building on campus. Our team consists of myself, Alex Dunholter, who's our CAD lead, Brian DeVito, who's our structural engineer focusing on the building foundations, Don Allis, who is our hydrology lead, Ethan Avila was the structural engineer focusing on the retaining wall, and Paul Lappin, who is our geotechnical lead. SDSU is planning to build a brand new North Life Sciences building to replace the existing structure on campus. The proposed site of development is a steep northeast facing slope on the northeast corner of SDSU's main campus. Currently, the site is heavily vegetated and will require extensive earthwork to make it suitable for the 5-story, 72,000 square foot structure to be built. Along with the retaining wall and the building foundations that are designed by Metal Engineering Consultants, there will be significant utility redesigns required for the project.
Hi, I'm Don Allis. I was the hydrology specialist for the project. I used the rational method, Q equals CIA, to solve for the flow rate, Q, to the site's point of discharge for a design storm event of 100-year, 6-hour. C is the runoff coefficient, obtained from this table based on the surface that water is flowing over. I is the intensity in inches per hour, and it's determined based on this chart for a duration equal to the time of concentration, which is the amount of time water takes to travel from the furthest edge of the project's drainage boundary to the point of discharge. This time of concentration was calculated based on the time water takes to flow over land into the inlet, in addition to the time that water spends traveling through pipes and channels. This was calculated based on the velocity of the flow within these pipes and channels. Overall, we were able to calculate time of concentration for each of the drainage areas of the site and obtain intensities therefore. The last term of the equation is A, which is the watershed area in acres. This area was delineated based on flow paths shown in the red arrows. For Area 3, all of the flow accumulates into this inlet before it can flow through this 18-inch storm drain to the point of discharge number 2. Putting this method into practice, we can calculate the peak flow to discharge number 2 for existing conditions. We obtain a result of 1.38 cubic feet per second. We apply the same method to the proposed conditions and obtain a runoff of 2.74 cubic feet per second. This indicates an increase in runoff of 1.02 cubic feet per second from the proposed site development. Now we need to ensure that the existing storm drain infrastructure is sufficient in size to handle this increase in flows. We do so using Manning's equation to solve for Q, the flow rate capacity. For the existing 18-inch corrugated storm drain, with a parameter shown, has a capacity of 15.76 cubic feet per second, which is much larger than the calculated peak flow of the proposed conditions. This indicates that the existing infrastructure is sufficient to handle all increases in flows. This allows us to proceed and design the drainage facilities for the site.
Hello, I'm Ethan Avila, and I am the lead structural engineer for the building's retaining wall. Our proposed 18,000 square foot wall reaches a maximum height of 50 feet and will require soil nails every 5 feet roughly, horizontally and vertically, with varied lengths depending on the depth of the wall to meet our design standards. We take our specific product parameters such as nail inclination of 15 degrees or a shotcrete with 4,500 psi strength and combine them with soil properties such as our cohesion of 200 psi or soil unit weight of 130 pcf to obtain an overall stability for the wall, total soil pressure moment, and surcharge weights. We then test for safety against overturning, sliding, and soil-bearing pressure, ensuring that our chosen specs meet requirements. These safety factors ensure that forces acting upon the wall will not cause bending, cracking, or failure, but instead would be contained in tension with our nails and grout bonding to the soil. After many tests and calculations, we are able to send the nail and wall details to our CAD specialists, Alex and Don, to create final plans.
Hi, my name is Alex Dunholter, and I was the CAD lead for our project. These are some of the sheets types that we drafted. Don and I mainly worked on these. This was the demolition plan, so we had to decide what we wanted to remain and what we wanted to remove. So some of the things that we had to remove was this power line here in the north end of the site and this storm drain here that was kind of the southern end. And here's a soil nail wall. So just again, I want to highlight some of the key points of our project. This was an interesting case because it was right under the bridge connecting Aztec Circle Drive as well as the new North Life Sciences building. and the micropile foundations of the bridge actually come through in the same section as the soil nail wall. So it's interesting to see how they overlapped. And we wanted to show that in our drawings. And that's on the left side. And on the right side, you can see a face-on view of our soil nail wall, one of the biggest sections of it. They're about all 5 feet from each other. And yeah, those are the highlights of the CAD.
Hi, I'm Paul Lappin, the geotechnical lead for the project. For the SDSU North Life Sciences Building project, understanding the site's geotechnical profile is crucial to safe and efficient design. The subsurface conditions include up to 20 feet of undocumented fill and residual soils, underlain by an Eocene cobble conglomerate and sandstone, and Cretaceous metavolcanic rock at depth. These materials present both opportunities and challenges, such as difficult excavation and potential for settlement. Groundwater is minimal, but perched seepage may occur at the fill formation contact. For design, key parameters include an ultimate bearing capacity of 5,000 psf for shallow foundations and 2,750 psf for the soil nail wall. With settlement estimated at less than 1 inch, corrosive soil conditions also necessitate the use of Type 2 cement. Altogether, these parameters shape the recommendations for shallow foundations and a 50-foot permanent soil nail wall to retain the steep slope and endure structural stability.
The building foundation consists of a two-way reinforced concrete slab and deep pile foundations. Using ASCE live load factors, the proposed building design and assumptions for the material strength and expected load on the foundation was calculated. The slab foundation design is a typical two-way reinforcement with 4,000 psi concrete and number 6 and number 5 rebar. The calculations were completed based on ACI standards. The deep pile foundations are 1 foot in diameter, drilled in concrete. They extend to the varied bedrock depth beneath the foundation. The end bearing capacity was calculated to a factor of safety greater than 3. Based on the assumption that the foundation is taking a uniform load, the 80 piles were mapped out accordingly across the foundation.
Touching on the cost portion of the project, it's important to consider that Metal Engineering was only responsible for our specific design scope. Therefore, the cost listed above is only a representation of the materials necessary for demolition, a storm drain redesign, not other utility redesigns, the retaining wall, the building foundations, and the BMPs and erosion controls used on site. Therefore, $1.4 million will not be an estimate reflective of the entire building, but rather our project specifically. And with that, all of us at Metal Engineering want to thank you for listening, and go Aztecs.